Hi, everyone. How are you all doing this evening? This talk will be a little different from others. I'll try to keep it as light and conceptual as possible and give you lots of examples so that it's easy to follow. How many of you all have heard of ETA? Okay. Probably I can see like 3 hands or so. Okay, how many of you have used Haskell before? Okay, cool. My name is Jyothsna Patnam. I'm the co-founder of TypeLead, a company behind the ETA programming language that also offers commercial support for production users. My interest lies between the space where user experience meets programming languages. Let me start the talk with a fun question, and I want to see how many of you can get it right. What is the most widely used functional programming language? Any answers? Take guesses, come on. Okay, I'll give you the answer. The answer is Excel. So millions of professionals around the world who are not just software engineers have used Excel at some point of time to solve their day-to-day problems. Children are taught the basics of Excel when they are learning computer science itself. Anybody who's come in touch with a computer has has learned Excel at some point of time. Here is a simple example how Excel looks like. The first column gives you the price per unit in dollars, and the second column gives you the quantity of the item you bought. And the third column gives you the total of the items, and this is computed by a formula or a function that multiplies the first 2 columns. The interesting part about Excel is it's stateless. Now, what does that mean? You do not have to worry about variables or invalid states in your application. So we as developers, we need the same thing. We need to just worry about our business logic and not worry about the plumbing that goes through. So since we're talking about Android programming itself, I want to go on a high level what an Android application looks like. An Android application consists of 4 components: the inputs, event handlers, state transitions, and side effects. The inputs feed into the event handlers, and the event handlers run some code and cause some state transitions and side effects. Now, I want to break this down more and help you understand what I mean by every component. Inputs. Inputs are a medium through which the user interacts with the application itself. They may be button presses in Android programming, taps, swipes, or gestures, etc. And event handlers are pieces of code that trigger the main business logic of the application. They may be, in Android, the API allows you to register handlers for lifecycle changes, like on create view state changes like set on click listener, key presses like set on key listener, and menu items like set on menu item click listener. Now, this event handlers will give you side effects and state transitions, which I'm going to speak about now. What are state transitions? Whenever there is a change in your program, especially with the fields, especially when there is a value change in the fields of your program, there is a state transition. When your application starts off, it starts with an initial value, and it keeps on updating. The state keeps on updating throughout the duration of the application. Side effects. We all know what side effects are, but let me break it down now. Side effects are those things which your application does not have direct control over. This can be requested only by the underlying operating system or the underlying framework. These side effects, a few examples of side effects are drawing to the screen, acquiring a database, or sending HTTP requests. So everything is fine, right? Like, the application goes from the inputs, event handlers, that causes the state transitions and side effects. This is fine only when you write a single one-off app with just has static requirements. But you have these managers who always have different priorities, and they give you features to add when you're still working on something at hand. So with all these external factors, you're always worried about introducing many event handlers, side effects, and state transitions. Don't you think it's a huge mess over time? Is there a way we can actually handle this mess with a lot of sanity? Yes, that is where functional reactive program comes in. You might have heard of libraries like Rx and reactive extensions. These libraries handle only discrete values, but they do not give you the same power as the proper FRP libraries can give you, because FRP libraries are capable of handling even continuous time. Sorry. Now let's talk about reactive programming, not functional reactive programming, reactive programming. Reactive programming is programming with streams of data instead of single values of data. So everything is a stream here. We've been throwing the word stream a lot. What is it exactly? Stream is a sequence of values which can grow throughout the duration of your application. Let's make it more concrete. Here are a few stream examples. The first one is a stream of button clicks. Whenever a user presses a button, an event is fired, and you can see it there. And the second one is a stream of text field modifications. Here is a simple example where the user is pressing T, and next he presses TO. With the modification, the entire text field is recorded here. And then he realizes that pressing O was a mistake, and so he deletes it. So this entire thing is recorded in a form of a stream. Now, let's talk about functional reactive programming after understanding what reactive programming is. We already spoke about reactive programming as discrete values of time. Okay, sorry about that. So functional reactive programming, the basic concepts are behaviors and events. Events are nothing but what we've discussed until now. They are streams of discrete values. On the other hand, behaviors are streams of continuous data. Behaviors can also be referred to as signals, which we are going to see, which is used extensively in the library we are going to speak in some time. An FRP system consists of a set of input signals that are transformed into an output signal. So here you have the signal network where some operation goes on, and that takes care of all the transformation. Before implementing a simple example in ETA, I would like to talk to you a little bit about what ETA is. ETA is a fork of Glasgow Haskell compiler that runs on the Java virtual machine. Most of the Haskell packages run without any changes in ETA, and few packages compile with few modifications. And our focus with ETA is to make it as effective as possible for industrial use. ETA's core language. ETA is a pure, lazy, statically typed functional programming language which interfaces with Java with a foreign function interface. That's a lot of jargon. Let me break it down. What does purity mean? A pure function is a function that gives you back the same output for a given input. Here is a simple example which calculates the price of a product after 20% discount. So for every given product price, the discounted price will always be the same. This is called purity. So this amazing property of pure functions has a lot of good benefits in everyday function, and one of them is it allows you to write modular code. That means one part of the code in your application is independent of the other, which helps you refactor fearlessly. Moving on to laziness. Laziness is an evaluation strategy in which whatever is required at a time is evaluated only and nothing more. Now let me give you an example in contrast with a strict language. Here is a simple expression where you have a list, you first transform the list by multiplying it by 2, and then take the sum of the list, resulting list. In a strict language, these are the reduction steps. First, that's like the normal way. You just multiply the entire list by 2, and then you take the transform list and take the resulting sum. In a lazy language, every pattern match forces an evaluation. What does that mean? When you take a list, when you pattern match on a list, it gives you access to the first element and the rest of the element. And so you can do recursion and so on. Here are the definitions of the sum and map functions. And here are the reduction steps of our example. By the way, this is just for illustration purposes. The compiler, ETA or Haskell compiler, doesn't have so many reduction steps. There are a lot more complicated, complex optimizations that go on, which I really don't want to speak now. OK. So on a high level, what exactly is happening here? The evaluation is happening bit by bit as opposed to the whole entirety. Now that we've understood what laziness is, let's see what's the practical benefit of laziness. Here is a simple example. This is a function, simple function, that checks if a list is empty or not. In case it's not empty, it prints the head of the list. Head of the list is the first element, by the way. So we programmers, we are human beings. And we do mistakes, we refactor so many times, and you never know. Say we actually introduce a binding called first by mistake that takes the head of the list here in front, just before the if condition. In a strict language, this might actually crash your program. But in a lazy language, the first expression, that is first, the binding itself, that expression won't get evaluated until it's used somewhere. So again, you can refactor safely and have the program fix the order for you, so you do not have to worry about it. This is one of the practical benefits. So let the data flow fix the order for you. Now, types. Types are everywhere in ETA. They are a way to label the data in your program so that you can describe precisely what your functions are doing. Here is a simple example. So this is from the ETA's REPL session. The first one is has a type character, and the second one is a list of characters, and the third one is called something called polymorphic literal, which can either take the type float or double depending on the situation. The interesting part of this slide is functions like plus and print can also have types in ETA. So being able to give types to every expression in your language means you can tell your functions what exactly you want to do and also help your compiler understand what you intend to. If your compiler understands you, it will help you prevent several classes of bugs at compile time itself. So types, the main benefit with types is they let you shift runtime errors to compile time, which is incredibly useful, especially when you're iterating fast on your applications. Now, I'll speak in brief about the interop with Java. The interesting challenge we had to solve was to interact with an object-oriented language by not compromising on ETA's core concepts like purity, laziness, etc. I'll show you how we made the interaction smooth. Here is a simple Java class called counter. It has a private integer field called counter. You can initialize it. You can increment it using the increment method, and you can get the current value using the get instance method. And you can also update it using the set instance method. The first thing when writing an ETA program is you have to import the Java module itself. This module consists of all the functions and the types required by the interop system. And the second step is to define something called the Java wrapper type. In this, this is where you actually treat a Java class as an ETA type. So it's basically telling the compiler you can treat this as an ETA type. We convert a Java class to an ETA type here. And the last step is you're going to write something called FFI imports for all the methods that are required by your application. This is the part where the impure Java methods are converted into pure ETA functions. Here, this is the converted Java code. By the way, this is like a one-off translation. I'm not going to cover how you can actually convert Java code to ETA code, but you can actually do it. So this is, OK, there you can see the Java function, which converts the Java expressions into an IO type unit so that our main function can use it. So you initialize, you create a new counter, initialize it to 10, and then you can do some state changes and print the final result over here. So let's be practical. Writing so many FFI imports it's really tedious. So one of our community member, he proposed something called the direct Java interop. So I told you there is a one-off way to do it. So we can automate this, and this work is being done right now. The compiler will take care of all the imports for you, and you just have to do this part. You don't have to do all this. The Java JWTs, that is the Java wrapper types, or even the FFI imports. You just have to concentrate on the business logic. And this will be out probably in a month or two, so yeah. This is where I can actually treat ETA as a better Java with additional benefits like purity, laziness, etc. Now that we've seen ETA, let's get our hands dirty and implement something. I've chosen the 2048 game. How many of you know what, how many of you have played a 2048 game before? Okay, that's pretty much everybody. Yeah? Okay, sorry. Yeah. This is a very simple puzzle game where you have to, you can just swipe up, down, left, and right. And the tiles have to match with each other so that they can combine to form a new tile, say 2 and 2 combine to give you 4. And yeah, the objective is to eventually make a tile with the number 2048. So in order to implement a game in ETA, we need ETA's integration into the Android Studio itself. We also need a way to create input signals with the Android event handlers. We need an FRP library that can convert input signals to output signals. We also need a way to take the output signal and render the game. I'm going to spend most of the time speaking about the FRP library used, and so that it'll help you understand how the game logic is written itself in ETA. Because if from this talk, if you just understand that FRP is mainly used for maintainability and declarative programming, that's more than enough. The first step is to start off an Android project as usual. The second step, in your root build.gradle file, you're going to include these lines of code. This is to help the Gradle plugin understand that an appropriate ETA version is required by your application. Here it's 0.8. And note that we also see a field called atlas version. Atlas is the build tool of ETA. And in the second step, we are going to include this code in your apps build.gradle file. The first one is to include the ETA Android plugin. The second part, between the Android, the entire area there, we're just including something called a progard file. A progard file is used to remove any dead code generated by ETA. And in the third part, we include all the dependencies. You can see that we have one Android library here, probably many of you are acquainted with, called RxSwipe, and the other are from the Haskell world. They are Yampa and Random. Now that our project is set up, let's get into the game logic itself. For this, I'm using a library called Yampa. This is proven to be a practical library in the Haskell world, and it's also used in production. Because of how ETA works, we get this library for free. We do not have to do any modifications. You can just compile it with ETA. So the two most important types used in Yampa are SF, that is the signal function, and event. So the SF and event. Yampa, the SF function, the signal function, it transforms the input signal into an output signal, and the library Yampa, it does not give you it does not allow you to create or operate on signals directly. You have to use the signal functions which are already in the library. A refers to the value produced by the input signal, and B refers to the value produced by the output signal over here. Now, this is the input for our game. So we define a data type called swipe event, which can take in 4 values. So what is the input for our game? It's just swipes, normal swipes. It's either up, down, right, or left. So this is defined over here. This is the data type from the Yampa library itself called event, which can either be a no event or event A. That is, no event is when no event is fired at all, and event A takes in some data and which actually tells you what exactly is happening when the event took place. Here is the function that has the entire game execution. So I'll just explain to you what's going on. The function's name is main SF. Yeah. So the game requires some randomness in order to give you a signal function that can convert an input signal to an output signal. So the proc do block you can see there. It allows you to represent any signal function in terms of other signal functions. So the swipe event you see here is an input to our parse input signal function and converts the swipe input to game input. And in the next step, the game input is an input to the whole game signal function and results in a game state. And the game state is taken as an input for into the draw game signal function, which renders our game itself. So on a high level, this is what is happening. The proc do block is similar to the do notation itself, but this is for something called as arrows. Before we talk about the whole game signal function, I want you to check for this function called switch. Switch, what is a switch? Practically speaking, just switching between two states. Here, this does exactly the same thing. Switch is a function which takes two signal functions and can act as the first signal until an event is fired. As soon as it's fired, it can act as the second signal. So until there is no space in our grid, the game is alive. But after there are no more tiles, like you cannot add any more tiles, the game over screen is shown and the game ends. So the first signal is represented using the proc do block here. And the second signal is the last part, the restart game signal function. That part is the second signal. Now, this is the game state itself. The game state data type has 4 fields. It can take board, score, status, and gen. Gen is it has a type std_gen, which is defined in the random library, which can help you give any randomness. Here, the game alive function, it can help you place 2 random blocks at the start of the game. So when you start a 2048 game, you have 2 random tiles which appear, right? So this is taken care over here. And the run game takes care of holding a state of the game itself. So whenever at every stage of your game, the state has to be held somewhere, stored somewhere. This is where that happens. The run game takes care of it. And update, this is the function that updates your game board. game board and also the score at any particular time. You can look at this. You can check this out. This is all on GitHub, the entire code. Yeah. So the interesting part about this entire implementation over here is that you could actually implement a game with just handful of functions and with no side effects at all. So FRP gives you that power. So you do not have to worry much about the underlying implementation, which the other libraries don't give you. So here is the link to the game itself. You can look into this later. So I want to tell you something really interesting. If you're not familiar with the Haskell world and the ETA world, you can write the game logic in Haskell or ETA because both are similar. And you can actually produce 3 types of application at the same time. Meaning, you write the game logic in Haskell. You can use the gloss Haskell package and make a native application, GUI application, and do a little modification, use the JavaFX API, and via that you can make with the same code, you can actually make a desktop, JVM desktop application, and use the same game logic with an Android API. You can actually make an Android game. So here I end my talk. Hope this helps you. Yeah, thank you.